Okay, good morning students. So today we are going to discuss with the numerical examples on damped free vibration. So in the previous video we have discussed the displacement response equation for damped free vibration. So depending upon the damping ratio, there are three different cases we have discussed. The damping ratio psi is equal to 1, it is a critically damped system. The damping ratio is greater than 1, it is called an overdamped system. And if the damping ratio is less than 1, it is an underdamped system. And the structure behaves, or the displacement response for these three different cases, we have derived the equations. Now we will deal with the numerical examples based on this. Question number 1. A mass of 1 kilogram is attached to the end of a spring with a stiffness 0.7 Newton per millimeter. Determine the critical damping coefficient. So the data given: mass is equal to 1 kilogram, stiffness of the system 0.7 Newton per millimeter. We are asked to find out the critical damping coefficient. So let us come to the solution part. The critical damping coefficient C suffix C is 2m omega, where omega is the natural frequency of the system in radians per second, is equal to root of k by m. So what is k? 0.7 Newton per millimeter. It has to be converted into Newton per meter, divided by the mass 1 kilogram. Will give you the natural frequency as 26.46 radian per second. Therefore, substituting in this expression, critical damping coefficient is 2m omega. It will work out to 52.92. The unit is Newton meter per second. It's a very simple example. Okay, we'll pass on to the second question. For a single degree of freedom system, mass is 10 kilogram, stiffness 6.25 kilonewton per meter, damping coefficient 20 Newton second per meter. At t is equal to 0, x0 is equal to 0, x0 dash is equal to 150 meter per second. Obtain the equation of motion and find the displacement at 2 seconds. So coming to this, the given data are mass 10 kilogram, stiffness 6.25, damping coefficient 20 Newton per second, Newton second per meter. At time t is equal to 0, x0 equals 0 and x0 dash 150 meter per second. So these are the data given to you. Asked to find out the displacement when time t is equal to 2 seconds. So based on the given data, we have to identify the system falls under which category, whether it is an underdamped system or overdamped system or critically damped system. Only then we can write down the equation of motion. The equation of motion is different for the three different cases. So let us first of all find out the solution. Find out the natural frequency of the system. Omega is equal to root of k by m. Here the k is given as 6.25 kilonewton per meter into 10 raised to 3 divided by mass 10 kilogram will give you 25 radian per second. Let us find out the damping coefficient C, the damping coefficient of the system. The damping coefficient C is given as 20 Newton second per meter. So the critical damping coefficient critical damping coefficient C suffix C, that is equal to 2m omega. 2 mass is given 10 and omega. So the critical damping coefficient C is equal to 2m omega. Then we find out the damping ratio. Damping ratio psi is equal to C by Cc. The ratio of the damping in the system to the critical damping coefficient is called damping ratio. So 20 divided by C by Cc will work out to 0.04. So the damping ratio of the system is 0.04, which is less than 1. So it is an underdamped system. The damping ratio is less than 1. It's an underdamped system. The equation of motion. The displacement response xt is equal to, for an underdamped system, e raised to minus psi omega t into c1 cos omega dt plus c2 sin omega dt. For an underdamped system, the displacement response equation of motion is, for a damped system, mx double dot plus cx dash plus kx is equal to 0. This is the equation of motion. From that we get the displacement. We have derived it. The displacement at any time is given by the expression e raised to minus psi omega t into c1 cos omega dt plus c2 sin omega dt. Where this omega d is called the damped frequency. That is equal to the natural frequency omega into root of 1 minus psi square. Substituting, omega was 25 into root of 1 minus psi square. It works out to 24.98 radians per second. So we can see that when the damping is very small, the damped frequency as well as natural frequency is almost the same values, very less. The damped frequency will be slightly less when compared to the undamped natural frequency or undamped frequency or the natural frequency. So omega d is 24.98 radians per second. So in this expression, we have to find out what is C1 and C2. For that, we are given the initial condition. To find the C1 and C2, the initial condition is at time t is equal to 0, the initial displacement is equal to 0. At time 0, x0, 0, and the initial velocity x0 dash is given as 150 meter per second. So substituting in this equation, at t is equal to 0, e raised to psi omega t, x0 is equal to 0. This term, e raised to 0 will become 1. Cos omega dt, cos 0 is 1, so c1. Plus c2 sin omega d, sin 0 is 0. So we will get c1 is equal to 0. Next we have to get c2. For that we differentiate this equation. Differentiating, x dash is equal to e raised to minus psi omega t. First into differential second. Differential second is c1 sin omega dt into omega d minus plus c2 cos omega dt into omega d. First into differential second plus second c1 cos omega dt plus c2 sin omega dt into differential of first. Differential of first is e raised to minus psi omega t into minus psi omega. This is what we have done in the derivation itself. In this, if you put t is equal to 0, by putting t is equal to 0 and x0 dash is 150, we'll get 150 is equal to, this will become 1, this is 0, this will become 1 into C2 omega d plus, in that expression, minus psi omega into C1. I'll write it here itself, x0 dash. Instead of x dash value, I'll put it as a x0 dash. At time t is equal to 0, it is x0 dash. From that you will get C2 is equal to, the C1 we have got, C1 will be usually x0, C1 is nothing but, here we have got that C1 is equal to x0, that is equal to 0. x0 plus theta omega x0 dash divided by omega d, C2 omega d. So this expression we have already derived while during the derivation. The coefficient C2 is x0 plus theta omega x0, theta omega x0, x0 dash plus, this is x0 dash plus the theta omega x0 will come here divided by omega d. So substituting these values, we will get C2 is equal to 150 x0 dash. Since x0 is 0, this will become 0 divided by omega d, 24.98, will work out to 6.005. Therefore, the displacement at any time, is equal to e raised to minus psi omega t into C1 cos omega dt plus C2 sin omega dt. In this, the C1 is 0, so first term vanishes. Second term is C2. C2 is 6.005 sin omega dt. So the displacement at any time is given by this expression. In this, you put t is equal to 2. Put t is equal to 2 seconds, and the sin omega dt, that should be in radians. Substituting the values, we will get the answer as minus 0.244 meter. We'll pass on to the question number 3. The amplitude of free vibration of a single degree of freedom system reduces from 5 millimeter to 2 millimeter in 10 cycles. Find the percentage of critical damping. So coming to the data, we are given the amplitude. Initial amplitude is 5 millimeter. It reduces to 2 millimeter after 10 cycles. So the 10th cycle, it reduces to 2 millimeter. We have seen it in the case of underdamped system. The amplitude of vibration goes on reducing with time. If the first one is x0, after 10 cycles, say after 10 cycles, so let it be x10, this is say x10, after 10 cycles it becomes 2 millimeter. You are asked to find out the coefficient of critical damping. Find the percentage of damping. Find the percentage of critical damping. What is the damping ratio? If we can find out that, we can say what is the percentage of damping present in the system. So we have mentioned that logarithmic decrement, a concept A logarithmic decrement, natural logarithm of two successive amplitudes x0 by x1. If the two successive amplitudes x0 by x1 is called the logarithmic decrement delta. Similarly, I can also write natural logarithm of, instead of x0 and x1, x1 by x2. That is also delta. Natural logarithm of x2 by x3. That is also delta. If I continue like this, the natural logarithm of x9 by x10. That is also delta. So you multiply all these together. From this I can write x0 by x1 is equal to e raised to delta. Isn't it? Natural logarithm. So if you take it, the result will be e raised to delta. Similarly, x1 by x2 is also e raised to delta. Similarly, x9 by x10, that is also equal to e raised to delta. So multiply all these together. x0 by x1 into x1 by x2 into x2 by x3 into etc. x9 by x10. That will be e raised to delta x to 10 delta. It will give us e raised to 10 delta. You multiply all these together, the right hand side, it will become e raised to 10 delta. Now you see, you can cancel this. Finally, can cancelling like this, we'll get x0 by x10 is equal to e raised to 10 delta. Or generalizing this, we can write xn, if it is the nth amplitude, divided by, or x0, the first one, divided by the nth cycle xn is equal to e raised to 10 delta. This is a general expression. If you know the first amplitude x0 and after n cycles where you say x suffix n, x0 by xn is equal to e raised to n delta. So coming to this, here x0 5 divided by the x10, it is 2, is equal to e raised to 10 delta. 5 by 2 is equal to x0 by x10 is equal to e raised to 10 delta, or e raised to 10 delta is equal to 5 by 2 is 2.5. From that you get what is 10 delta. 10 delta is natural logarithm of 2.5. And from that we get this is 0.916. And delta is equal to 916 or 926. Therefore, delta is equal to 0.0926. And we have the relation, we have derived it. Delta, the natural logarithm of two successive amplitudes is called delta. Then delta is equal to 2 pi psi. From that we get the damping ratio psi is equal to delta by 2 pi. So delta 0.0926 divided by 2 pi will give you the damping ratio 0.0146. Therefore, the percentage of damping, the percentage critical damping is equal to, percentage damping is this into 100. This into 100, that is 1.46 percentage. Thus, we have illustrated that the logarithmic decrement is a means for measuring the damping present in the system. By giving the system a vibration, if you measure the two successive amplitudes or the amplitude after n number of cycles, we can calculate what is the damping present in the system. This is an illustrative example. So the next question, question number 4, similar to the previous one, the damping ratio of a single degree of freedom system is 0.005. Find the number of cycles required to reduce the amplitude by 50%. So here it is given the damping ratio. So here it is given the damping ratio of the system is 0.005. We are asked to find out number of cycles which is required to reduce the amplitude by 50%. So let us assume the initial amplitude x0 and the final amplitude 50% of this is reduced by 50%. So the final amplitude is 0.5x0. So we have x0 by xn is equal to e raised to n delta, or x0 by 0.5x0 is equal to e raised to n delta. We are asked to find out n. What is delta? The logarithmic decrement is 2 pi psi. 2 pi, we are given psi 0.005. So substituting, we'll get x0 by 0.5x0 is equal to e raised to n delta is 0.0314. So taking natural logarithm, we'll get natural logarithm of, we'll take natural logarithm of both sides. Natural logarithm of 1 by 0.5 is n into 0.0314. Therefore, we get n is equal to 22.07. That is 22 cycles. So the amplitude will reduce to 50% in 22 cycles. So coming to question number 5. A simply supported girder of span 3.5 meter and mass 87.5 kilogram was subjected to a concentrated impulsive force at midspan. In the free damped oscillation which followed, the ratio of to successive amplitude of the girder at center was 1.3. Calculate the time taken for the amplitude of vibration to decay to 1 by 50th of initial displacement. Given the moment of inertia 2290 centimeter raised to 4, Young's modulus 200 kilonewton per mm square. Also compute the coefficient of damping. So coming to the solution part, we are given a simply supported beam of span 3.5 meter. A simply supported beam of span 3.5 meter. It is subjected to a central load W and the mass of the beam is 87.5 kilogram. So a simply supported beam is subject to a central load here and it starts vibrating. And the ratio of the two successive amplitude was 1.3. That is, once it is vibrated, the next amplitude is also noted. So we are given x0 by x1, the two successive amplitude is 1.3. We calculate the time taken for the amplitude of vibration to decay to 1/50th of. So when xn is 1 by 50th of x0, we are asked to find out what is the number of cycles required for that. So let us come to the question. A simply supported beam with central point load. This deflection, I'll mark it as delta. Small this delta. Deflection is W LQ by 48 EI. The simply supported beam with central load. W LQ by 48 EI is the central deflection. So the stiffness of the beam stiffness of the beam is equal to W by delta, or it will be 48 EI by L cube. So substituting the given values, E and I are given in the question. Length is given as 3.5 meter. The span is 3.5 meter. E is given as 200 kilonewton per mm square. And I is given as 2290 centimeter raised to 4. So substitute the values with proper units. All the units should be in meters, and you will get the answer as stiffness of the beam 5.127 into 10 raised to 6 Newton per meter. So we have the stiffness of the beam, so we can calculate what is the natural frequency. Omega is equal to root of K by M. So substituting this value, root of K by M, K is here, M is here, so you get the natural frequency 242.07 radian per second. Now we are given x0 by x1. x0 by x1 is equal to e raised to 1 delta. Now that is equal to e raised to delta. That is 1.3. Natural logarithm of 1.3 is equal to delta, and that is equal to 0.262. You got the logarithmic decrement. Now delta is equal to 2 pi psi. Therefore, the damping ratio is equal to delta by 2 pi. Will work out to 0.0417. We'll get the damping ratio of the system. Then now we can get the damped frequency omega d is equal to omega into root of 1 minus psi square. Substituting these values, 241.86 radian per second. So we have got the damped frequency. So what is the time period? Damped time period. Omega into t is 2 pi. So it is 2 pi by omega d will work out to 0.026 seconds. So what does this mean? For the system which is subjected to all these conditions, the time taken for one cycle in damped free vibration, time for one cycle is 0.026 seconds. So time period means time for one cycle. Now we are given what is the time required for the amplitude to reduce 1/50th of the initial amplitude. So we have x0 by xn, that is x0 by 50. Xn is equal to e raised to n delta, and delta value is 0.262. That is e raised to 0.262 n is equal to 50. So 0.262 n is natural logarithm of 50. From that we get n is 14.93 cycles. So the amplitude gets reduced to 1/50th of the initial amplitude in 14.93 cycles. The time required for one cycle is 0.026 seconds. So from the initial amplitude to reduce the amplitude to 1/50th of the initial value, the total time required, total time required will be equal to number of cycles into the time for one cycle. So it will work out to number of cycles is 14.93 cycle. The time for one cycle is 0.026. So it works out to 0.387 seconds. The next question number 6. For a single degree of freedom system, M is equal to 50 kilogram, the stiffness 20 kilonewton per meter, coefficient of damping C 3 kilonewton second per meter. If the initial displacement x0 is equal to 0 and x0 dash is 150 millimeter per second, obtain the equation of motion and find the displacement at t is equal to 1 second. So let us see what are the given data. Mass 50 kilogram, stiffness 20 kilonewton per meter, coefficient of damping C 3 kilonewton second per meter, x0 the initial displacement 0 and the initial velocity x0 dash 150 millimeter per second. We are asked to find the equation of motion and find, the question is find the displacement when t is equal to 1 second. So first step is we will pass on to the solution part. Find out the natural frequency of the system. That's always the first step. Omega is equal to root of k by m. K is given as 20 kilonewton per meter. So it is into 10 raised to 3 newton per meter divided by mass 50. You will get the natural frequency of the system 20 radian per second. Then calculate the damping ratio. Damping ratio psi is equal to C by Cc, or it is C by 2m omega. C is given as 3 into 10 raised to 3 Newton second per meter, to m 50 and omega 20. Substituting these values, we will get the damping ratio 1.5. So this is greater than 1. We call it as an overdamped system. So the system is overdamped based on the properties given. It's an overdamped system. So the equation of motion for a mx double dot plus cx dot plus kx is equal to 0. And the solution for an overdamped system is x is equal to a1 e raised to lambda 1t plus a2 e raised to lambda 2t. What are these lambda values? The lambda 1, 2 values are minus c by 2m plus or minus root of c by 2m the whole square plus minus omega square, c by 2m the whole square minus omega square. These are the roots of this equation, and based on this value of c by 2m and omega, we have classified it into underdamped, critically damped and overdamped. So when c by 2m is greater than omega, this will become positive. So there will be two different roots, lambda 1 and lambda 2. One will be obtained by plus and the second root will be obtained by putting the minus sign. So let us substitute. All these values are available now. You substituting c, m, omega, everything in this, you will get lambda, will get minus 52.36 and the second root as minus 7.64. So this is say lambda 1, say this is say lambda 2. we'll get the two roots. So take it as true as 1. By adding this, we'll get this is the first one. By subtracting so we'll get the two roots, minus 52.36 and minus 7.64. So the equation of motion or the displacement equation is x at any time is equal to a1 e raised to minus 7.64 t plus a2 e raised to minus 52.36 t. That's the first part of the answer. Here you have to find out the coefficients a1 and a2. For that we are given the initial conditions, x0 is equal to 0 and x0 dash is equal to 150 millimeter second. So next we are going to evaluate the constants a1 and a2 in this expression. At x is equal to 0, t is equal to 0, x0 is equal to 0. Substituting 0 is equal to a1 e raised to 0, a1 e raised to 0, 1. a1 plus a2 is equal to 0. That is the first equation. Or we'll get a1 is equal to, from that we can write a1 is minus of a2. Now we differentiate this, differentiating x dash a1 e raised to minus 7.64 t into minus 7.64 plus a2 e raised to minus 52.36 t into minus 52.36. Putting t is equal to 0 in this expression. Putting t is equal to 0, this will become 150. At t is equal to 0, this is 150. This will become 1 minus 7.64 a1. This will become 1 minus 52.36 a2. And we have a1 equal to minus a2. So this will, substituting here, this a1 equal to minus of a2, we'll get 150. This is the second equation. Solving this, we'll get a1 is equal to 3.35 and a2 is equal to minus 3.35. So the equation is x at any time is equal to 3.35 e raised to minus 7.64 t minus 3.35 e raised to minus 52.36 t. This is the final solution or the motion equation of motion. Now we are asked to find out the displacement at 1 second. So put t is equal to 1 in this expression. We will get x when t is equal to 1 is equal to 3.35 e raised to minus 7.64 into 1 minus 3.35 e raised to minus 52.36 into 1, and it will work out to 1.61 into 10 raised to minus 3. Here the velocity is given in millimeter per second. We will get the answer as 1.61 millimeter. So with that we complete the numerical examples on damped free vibration. So next video we will be dealing with forced vibration of undamped as well as damped systems. Thank you.